Hello, welcome back to this series of lectures on numerical optimization. So, in the last class, we started studying about steepest descent method. So, in the steepest descent method, the idea is to move along the direction of steepest descent. So, we use the first order approximation of the objective function, and then the steepest descent direction is the negative of the gradient direction. So, we saw that if these are the contours of the objective function, and if we are currently at a point which we call it as xk. Now, this is the first order approximation, this is the gradient at that xk, and with respect to the first order approximation, the maximum decrease in the objective function is possible when we move along the negative of the gradient direction. So, if we move along this direction, then we get the maximum decrease in the first order approximation of the objective function. So, the direction dk is equal to minus of gk is called the steepest descent direction. So, we will denote it by a subscript SD. So, at the kth iteration, the steepest descent direction is nothing but the negative of the gradient direction. Then along with that direction, if we use line search, then we have the steepest descent algorithm with line search. So, let us continue our discussion on the steepest descent method. So, as I mentioned, the steepest descent direction is at the kth iteration is nothing but the negative of the gradient at that point, and the steepest descent algorithm starts with the usual initialization of x0, the tolerance for the norm of the gradient for used for stopping, and the iteration number is set to 0. So, while the norm of the gradient is greater than epsilon, which is the direction dk to be minus gk, and this is the thing but the steepest descent direction. And then one can use one can find the step length of positive length such that the value of the objective function at xk plus alpha k dk is less than f of xk, and alpha k satisfies Armeyhov-Wolff conditions. Remember that these conditions are necessary to ensure convergence of an optimization algorithm. These conditions along with the condition that the direction is a descent direction, and then the xk is moved to xk plus 1 by adding alpha k dk. The iteration counter is incremented by 1, and then the whole procedure is repeated till the norm of the gradient at a given point xk is less than or equal to epsilon, and at that point the algorithm stops, and as a output we get x star, which is nothing but the xk, which is a stationary point of f of x. And then we started looking at some of the examples. Note that the exact or backtracking line search also can be used in step 2b rather than the two steps which are mentioned here. We can use the backtracking line search or exact line search. We studied backtracking line search in the last class, so those ideas can be used in step 2b of this algorithm. Now, then we started looking at some of the examples. So, the first example we took was of a function f of x, which is defined as x1 minus 7 square plus x2 minus 2 square. Now, the gradient of the function is 2 into x1 minus 7 and 2 into x2 minus 2, and the point at which the gradient vanishes is 7 comma 2, or whose x coordinate is 7, y coordinate is 2. The Hessian matrix is also given here. Now, this is a quadratic function, though, so Hessian matrix is independent of x. So, the x star is a local minimum. And if you look at the contours of this objective function, so here the objective function value is 8. So, this contour this curve corresponds to the objective function value of 8, and then the objective function value comes down to 4, 2, 1.5, and finally at the point 7, 2 we have the minimum of the objective function. And let us apply steepest descent method to this objective function. Now, suppose if we start from a point which is 9, 4 and apply steepest descent method with exact line search to the objective function, then you will see that in one step we have reached the solution. Now, were we lucky to start with this particular initial point? Let us find out. Let us take another, let us take the same function, but another initial point. So, we have taken the initial point whose x coordinate is 5.5 and y coordinate is 3, and you will see that again in one step the steepest descent algorithm converges to x star. So, if we have circular contours of a quadratic function, then the steepest descent method would converge to x star in one iteration. Now, let us see when the contours of a objective function which is quadratic are not circular, but they are elliptical. So, let us look at another example. So, we have a function 4x1 square plus x2 square minus 2x1 x2. The gradient is 8x1 minus 2x2 and 2x2 minus 2x1. Now, the gradient of this objective function vanishes at the origin. So, that is a stationary point, and you will see that the Hessian matrix is a positive definite matrix. So, the origin is a strict local minimum of this problem. So, let us look at the contours of this objective function. So, we can see this contour plot of f of x. So, this is the plot corresponding to the objective function value f of x equal to 8, and as we move inside the objective function value decreases. So, from 4 to 1.5, 0.1, and finally, we get a 0 objective function value at the origin. So, origin is a strict local minimum of f of x, which is given here. Now, let us apply the steepest descent algorithm to this objective function with exact line search. Now, if we start from this point which whose x coordinate is -1 and y coordinate is -2. So, and if we apply exact line search, so the first point that we reach from this initial point is this point, and then we move along this direction and so on and so forth. So, more than 20 iterations were needed in this case to reach from -1 to from -1, -2 to 0, 0, if we use steepest descent method with exact line search. Now, you will see that the behavior, if we apply the steepest descent method in this case, we will see that the iterates are formed in the zigzag directions before the convergence to the optimal point takes place. So, this zigzagging behavior is very typical of steepest descent method for quadratic functions, where the contours of the quadratic functions are not circular. Now, why does this zigzagging take place? So, we will study that in today's lecture. Now, compare this with the one step convergence for the circular contours. So, if the contours were circular, starting from any point we could converge to the minimum in only one iteration, while here if the some contours are elliptical, then we require more number of iterations. And we will see that if we start with another point, again in this case about 4 iterations were needed. If we started from this point whose x coordinate is 1 and y coordinate is 0, and about 4 iterations were needed before the steepest descent method converges to the minimum of this objective function. So, what is so special about these elliptical contours which make the steepest descent method with exact line search behave in this particular way? That is, what is the reason behind this zigzagging directions that we get from steepest descent method applied to the quadratic functions which have elliptical contours. So, we will study that now. Now, before that, let us take another example. This is a standard function which is used in optimization literature to study the performance of different optimization algorithms. And so, the Rosenbrock function which we studied in one of the earlier classes is given here, and we know that the minimum of this objective function occurs at 1, 1 and the minimum objective function value is 0. Let us look at the contours of this. So, the outermost plot corresponds to the function value 16 and then comes down to 8, 4, 2, 1 and finally, this is the point which is shown by the red star. That point is a minimum of this function. Now, let us apply steepest descent method to the function f of x, and this time we will use the backtracking line search. Okay. So, if we start from a point 0.6, so you will see that the first step is to this point and then to this point, and then there are lots of small steps. So, there are lots of small steps which correspond to the circles along these lines, and then finally, it goes and converges to the minimum which is 1, 1. Okay. So, lots of small steps are taken before the algorithm converges to the minimum. Now, here I have used backtracking line search. One can use any other inexact line search method. The number of steps required could reduce, but this is just to demonstrate that how the steepest descent method applied to Rosenbrock function with backtracking line search behaves when we start from a particular point 0.6. Now, let us take another initial point and see how is the behavior of steepest descent method with backtracking line search to Rosenbrock function. So, this is the Rosenbrock function, and suppose we start from -1.2 and 1. So, the first step that is taken is to this point, then the second step comes back to this point, and then you will see lot of small steps before the algorithm takes a big step to this point, and then again lot of small steps, then again a reasonably big step, and then lot of small steps. So, you will see that here the step sizes are really small before finally the algorithm converges. Okay. So, a lot depends on initial point, especially the number of steps needed to reach the final point depends a lot on the initial point. Now, let us go back to the previous example where we started from 0.6 and reached the minimum, and let us look at the behavior of the algorithm for this particular problem. So, here is a table which denotes the iteration number in the first column, then the coordinates at that particular iteration, then the value of the objective function, the distance between xk and x star, the Euclidean distance, and the norm of gk. So, initially k equal to 0 and we started with the point 0.6. the objective function value is 5.92, the distance between xk and x star is 0.5657 and norm of gk is 75.59. Now, the steepest descent method with backtracking line search required 2028 iterations in this case to reach an optimal, to reach very close to the optimal point, which is 1, 1. So, you will see that we have reached here to a point 0.99, which is reasonably close to 1, 1, and the value of the objective function is very close to 0. The distance between xk and x star is of the order of 0.0024 and norm of gk is 9.97 into 10 to the power minus 4. So, in this case I have used epsilon to be 10 to the power minus 3 in the steepest descent algorithm. So, the algorithm will continue till norm of gk becomes less than 10 to the power minus 3. So, you will see that at this step 2028 step, the algorithm has indeed gone to a stage where the norm of the gk goes below 10 to the power minus 3. So, I have shown here some iterations. So, you will see that from the initial point to the 10th iteration, there is quite a bit of reduction in the norm of the gradient from 75 to 0.39, and then from 10 to 100 iteration there is a gradual decrease in the norm. Again from 100 to 1000 there is a gradual decrease. So, the steepest descent algorithm in this case required about 2000 iterations to go to the minimum of this Rosenbrock function starting from 0.6 to 0.6, and every time you would see that the function value has been decreasing in a consistent way, although there could be a the rate of decrease could be very small, but there has been a consistent decrease in the objective function, and the distance from xk to x star also comes down at a reasonable rate. So, for the backtracking line search we need some parameters like alpha hat and rho. So, in this particular case I had set alpha hat to be 0.5 and rho to be 0.3, and the constant C1 which corresponds to Armyho's conditions was set to 10 to the power minus 4. So, this was with respect to the initial point 0.6, 0.6. Now, if we turn to the other example where the initial point was minus 1.2 and 1, and as we have seen here it requires lot more steps to go to the minimum. So, let us study the behavior of this algorithm. So, you will see that the algorithm required about 2300 iterations before it reached close to the minimum. Remember that minimum is 1, 1, and the point that we have reached is 0.9989, 0.9979, which is reasonably close to 1, 1. So, the distance between the xk and x star is about 0.0024, and as in the previous case these two columns denote the coordinates of points at the kth iteration, and this column denotes the distance between xk and x star, and this column denotes the norm of gk. So, you will see that initially the norm of gk when we started with this point, the norm gk was 232.87, and that came down to 7.69 and then 0.4. Finally, when the algorithm terminated, the norm of gk was less than 10 to the power minus 3, and in this particular case the value was 9.63 into 10 to the power minus 4. You will also see that the distance of xk from x star gradually came down to 0.0024, and the value of the objective function finally was almost close to 0, which is the desired objective function value. Again in this steepest descent method, I have used backtracking line search where alpha hat again was chosen to be 0.5, rho was 0.3, and then the constant C1 was like in the previous case set to 10 to the power minus 4. So, you will see that the number of iterations needed depend a lot on the initial point x 0. So, you can also try applying steepest descent method to different objective functions and study its behavior. Now let us look at the quadratic case or quadratic function case and see how the steepest descent method converges to the minimum. Now, this particular case is very important because even if a function is non-quadratic, then somewhere near the optimal point x star, the behavior of the function is quadratic. So, it is important to study the behavior of the steepest descent method for quadratic case first before we move on to a non-quadratic case. So, let us consider the problem to minimize f of x, where f of x is defined as half of x transpose h x minus c transpose x, and H is a symmetric positive definite matrix. So, this is a convex quadratic function, and so the reason for studying this quadratic functions is that for many functions, even if they are non-quadratic, near x star or near their minimum, the behavior of the function is like a quadratic function. So, it is important to study the convergence of steepest descent method for a quadratic case. So, that is why I have chosen a quadratic function here first. Now, we know that the gradient of this function is h x minus c, and if we set the gradient to 0, so h x minus c equal to 0 gives x star to be h inverse c. So, this is the optimal point, and since it is a positive, H is a positive definite matrix, the inverse of H is possible, and we get x star to be H inverse c. Now, we want to see how does steepest descent method perform applied to this particular function f of x. So, in the steepest descent method, we have seen that in every iteration the direction chosen is a negative of the gradient direction. Now, for a quadratic function like this, we can also try using exact line search, because one can work out the exact formula for alpha k at every iteration. So, let us assume that we use exact line search in each iteration. So, this is an important assumption that we make, that exact line search is done in every iteration, and we use a steepest descent direction in every iteration. Now, with this, let us study the behavior of steepest descent method as applied to this convex quadratic function. As I mentioned that it is easy to calculate the step length alpha k at every iteration k if we use exact line search for quadratic function. So, let us see how to do that. So, we have f of x to be half of x transpose h x minus c transpose x, and the gradient at the point x k, we are going to denote it as denoted by g k, and that gradient is h x k minus c. Now, the descent direction is dk is minus g k. So, once we choose the direction, we need to find out what is the value of the step length. So, for that purpose, we define a function phi alpha, which is f of x k plus alpha dk, and we want to find out what is the value of alpha or what is the value of positive alpha such that this function is minimized. So, that positive value of alpha which minimizes this function will be the alpha k for this case. Now, since we are talking about a steepest descent method, dk is nothing but minus gk. So, phi alpha is nothing but f of x k minus alpha gk, and in the exact line search, the alpha k is determined by minimizing phi alpha. Now, in our case, f is a quadratic function. So, phi alpha also will be a quadratic function of alpha, and its minimum can be easily found out by setting phi dash alpha to 0, and setting phi dash alpha to 0. So, what we get is the gradient of f at x k minus alpha g k transpose minus g k equal to 0, and if you rearrange the terms, so gradient of f of x k minus alpha g k is nothing but h x k minus alpha h g k minus c transpose g k. Now, because remember that the gradient of x at k is h x k minus c, and so we can use the same formula here with x k replaced by x k minus alpha g k. Now, if we combine h x k minus c, so what we get is that is nothing but the gradient at x k, and which we can write it as g k. So, this quantity can be written as g k minus alpha h g k transpose g k equal to 0. So, h s k and minus c are combined to get g k, and this gives us the formula for alpha k, which is nothing but g k transpose g k divided by g k transpose h g k. Now, remember that H is a positive definite matrix which is symmetric. So, g k transpose h g k is greater than 0 if g k is not equal to 0, and g k transpose g k is a norm square, that is also a quantity which is greater than 0 if g k not equal to 0. So, if g k is not equal to 0, alpha k is greater than 0, and then we can use this alpha k to determine our x k plus 1, the new point. So, the new point x k plus 1 is nothing but the old point minus alpha k g k. So, the alpha k is the quantity which we derived just now into g k. So, that gives us the new point x k plus 1. Okay. Now, once we find the direction d k which is minus g k and find alpha k using the closed form solution that we have seen. Now, we are interested in finding out at what rate does x k converge. So, let us define a function e of x k to be half of x k minus x star transpose h into x k minus x star. Now, this function you will see that this is function is greater than 0 if x k is not equal to x star, that is because h is a positive definite matrix. So, e of x k is always greater than 0. So, that is one important point about this function e. We can also call it as a error function, because we can write e of x k as f of x k plus some constant. So, as we have seen earlier that sometimes the behavior of an optimization algorithm can be determined using some error function, and an error function can be the objective function that we want to optimize. So, minimization of f of x will be same as minimization of e of x, because f of x is just added to this constant quantity to get e of x. So, let us now study the behavior of steepest descent algorithm with respect to this function e of x. And remember that we are not losing anything, because e of x is nothing but f of x plus constant. The reason why e of x is chosen is that because of the nice form it has. So, this function is positive when x k is not equal to x star, and when x k equal to x star, the function is 0. So, we will see what happens to e of x k when the steepest descent method is applied to minimize f of x. Now, to study that, let us first define a variable y k to be x k minus x star, and so we can write h y k to be h x k minus h x star, and h x star is nothing but c. So, h x k minus c is nothing but the gradient of the objective function at x k, and that is nothing but g k. So, we will use this property that hyk equal to gk in deriving this expression. Now, we have already seen that the new point xk plus 1 is obtained by xk minus alpha k gk, and alpha k has a closed form solution which is gk transpose gk divided by gk transpose hgk. Now, if we use this, then we are interested in finding out what is the relative decrease in the function e when we go from xk to xk plus 1. So, in other words, we are interested in finding out what is e of xk minus e of xk plus 1 by e of xk. Remember that we are trying to minimize the function e. So, e of xk is greater than e of xk plus 1, because we are minimizing the function e. Secondly, e of xk is always greater than 0 when xk not equal to x star. So, assuming that xk is not equal to x star, this quantity is going to be always positive, and we want to see how it approaches towards the how the sequence xk approaches towards the optimal point x star. Now, so if we use this definition of e of xk, and since the factor half is common both in the numerator and denominator, so we can get rid of that factor, and what we get is xk minus x star transpose h into xk minus x star minus e of xk plus 1 is nothing but xk plus 1 minus x star transpose h into xk plus 1 minus x star, and in the denominator I have replaced xk minus x star by yk. So, what we have is yk transpose h into yk. Now, let us simplify this expression further, and so if we simplify this, what we get is 2 alpha k gk transpose gk minus alpha k square gk transpose h gk divided by yk transpose h yk. And now, we can plug in the value of alpha k that we have already found for this quadratic function, and if we plug in this value of alpha k that we have already found here, what we get is e of xk minus e of xk plus 1 divided by e of xk, which is a relative decrease in e, is nothing but this quantity. Now, this quantity is still dependent on the matrix H and H inverse. So, if you look at this expression, this is gk transpose H inverse gk. So, this the relative decrease in E depends on H, H inverse and gk. Now, can we get a bound on this relative decrease which is independent of this H? Now, one possible thing that we can do is that we can choose gk to be a norm 1 vector, so that gk transpose gk is 1. Now, can we get some bound on this which depends on H and H inverse? Now, if we can do that, then this we can bound the relative decrease in the objective function. Now, for that purpose we will need what is called Kantorovich inequality. So, let us look at Kantorovich inequality. So, let H be a symmetric positive definite matrix, and let lambda 1 and lambda n be the respectively the smallest and largest eigenvalues of H. Then for any x which is non-zero, this inequality holds. So, x transpose x square divided by x transpose h x into x transpose h inverse x is greater than or equal to 4 into lambda 1 lambda n divided by lambda 1 plus lambda n square, where lambda 1 is the smallest eigenvalue of H and lambda n is the largest eigenvalue of H. Now, if you compare this left hand side expression with the expression that we got here, we will see that they are same, where x is replaced by gk, and remember that our algorithm converges only at a point when gk is close to 0. So, as long as gk is not 0, we can write this quantity to be greater than or equal to 4 lambda 1 lambda n divided by lambda 1 plus lambda n square. Now, this inequality can be derived in different ways. There exist different proofs to prove this inequality. So, one of the proofs what it assumes is that x transpose x is 1, and then it tries to maximize this x transpose h x into x transpose h inverse x, subject to the constraint that x transpose x equal to 1. So, for that proof we require some knowledge about how to solve a constraint optimization problem. So, so let us postpone the discussion on Kantorowicz inequality till we study something about constraint optimization problem. So, for the time being, let us assume that this inequality holds and we can use it for our purpose. So, if we use this inequality, then the relative decrease in the function E, which is nothing but gk transpose gk square by gk transpose h gk into gk transpose h inverse gk, which is same as this when gk is not 0, and that is bounded by 4 lambda 1 lambda n by lambda 1 plus lambda n square. So, now the h on the right side of this equation are replaced by the the smallest and the largest eigenvalues of h. So, therefore, we can rewrite this expression as E of x k plus 1 is less than or equal to lambda n minus lambda 1 by lambda n plus lambda 1 square into E of x k. Now, H is a positive definite matrix. So, all its eigenvalues are positive. So, lambda 1 and lambda n both are positive and lambda n is greater than lambda 1. So, if you look at the expression here, lambda n minus lambda 1 is a positive quantity, lambda n plus lambda 1 is a positive quantity, and moreover lambda n minus lambda 1 is less than lambda n plus lambda 1. So, that is why lambda n minus lambda 1 by lambda n plus lambda 1 is a positive fraction. So, you will see that E of x k plus 1 is less than or equal to this fraction square into E of x k. So, that means that E of x k plus 1, E of x k is a decreasing sequence. E of x k plus 1 is less than E of x k. So, therefore, we have a decreasing sequence and E of x k is a quantity which is bounded below by 0. So, we have decreasing sequence of E of x k, that sequence will tend to 0 and x k will tend to x star. So, when this E of x k goes to 0, we have x k which goes to x star, because H is a positive definite matrix. So, with respect to E, the steepest descent method converges linearly. So, you can see that the definition of linear convergence holds with respect to E when the steepest descent method is applied to a convex quadratic objective function. Now, the convergence rate is no greater than this quantity, which is lambda n minus lambda 1 by lambda n plus lambda 1 square. So, that means the convergence rate depends on the smallest and the largest eigenvalues of the Hessian matrix of the quadratic function, and the rate is not greater than this quantity. The actual convergence rate, it does depend upon x naught. So, we saw earlier that different x naught for elliptical contours will result in different convergence rates for a quadratic function. Now, if we define the condition number of the matrix H to be the ratio of the largest and the smallest eigenvalue of the matrix H. So, let us denote this ratio by R. Then the convergence rate of a steepest descent method, it depends on R minus 1 by R plus 1 or the condition number of the matrix H. So, this is a very important observation that the condition number of the Hessian matrix of a quadratic function decides the convergence rate of the steepest descent method. Now, when this ratio is 1, when lambda n equal to lambda 1, then what we have is this quantity is 0 and then E of x k plus 1 will be 0. So, irrespective of your initial point, one goes to the minimum in one iteration. And when is this ratio 1? When lambda n equal to lambda 1. That means that when we have circular contours. So, that is why we saw that when we considered circular contours and wanted to minimize the objective function using steepest descent method, the convergence took place only in one iteration irrespective of the starting point. So, if we have r equal to 1 which corresponds to circular contours, then the convergence of steepest descent method required only one iteration. On the other hand, if r is much greater than 1, so which corresponds to the elliptical contours, and in that case we saw that the convergence required many more iterations before the algorithm reached the point x star. So, in that case the convergence is very slow. So, the convergence of the steepest descent method, although it is a linear convergence, the rate of the convergence depends on the nature of the contours of the quadratic function. So, if we have circular contours, we have convergence in one iteration irrespective of the starting point, and if we have elliptical contours, then the convergence is slow. A lot depends on the initial point. Now, for non-quadratic functions, as I said that at the minimum x star, the behavior of the function is typically like a quadratic function, and therefore, the rate of convergence of steepest descent method to x star depends upon the condition number of the Hessian matrix evaluated at x star. Okay. So, this is a very important point for non-quadratic function, and the theory that we saw with respect to the quadratic functions typically holds near the point x star. So, that is why it was important to study this theory, so that the result can be used for non-quadratic functions as well. Now, if we consider the same example that we saw earlier. So, we have taken the function x1 minus a1 square plus x2 minus 2 square, and we have applied steepest descent algorithm with exact line search, and you will see that it converged to the optimum point in exactly one iteration. And then we also saw other example where if we start from some other point, it again reaches the convergence in one iteration. Now, if we look at this objective function whose contours are elliptical, we saw that the zigzagging phenomenon occurs, and the steepest descent method in this case required many more iterations before it converged to the minimum. Now, what is so special about the circular contours which made the steepest descent method converge in one step, while in elliptical contours it required more iterations. So, let us try to analyze that. So, let us consider the problem to minimize f of x to be half x transpose h minus c transpose x, where H is a symmetric positive definite matrix, and we saw that the condition number of the Hessian matrix H, which is a positive definite matrix in this case, it controls the convergence rate of steepest descent method. And we also saw that if the Hessian matrix is identity matrix, that means that the condition number is 1, then the convergence of the steepest descent method is fast. Now, can we use this fact to derive a method which will be faster even if we use steepest descent method. So, let us consider a simple case. So, suppose what we have here in the first case we had circular contours, and in the second case suppose we have elliptical contours. Now, if we have for a quadratic function, if we have elliptical contours like this, we know that the steepest descent method does have slow convergence, especially when the contours are elongated. Now, can we convert or transform these contours to the circular contours, so that if we use the steepest descent method, we will get the convergence in one iteration. In other words, so suppose we have a function which is half of x transpose h x Suppose we have a simple function like this. Now, can we convert it to a function where we can write it as y transpose y. So, suppose we have done some transformation. So, let us call this as x space, and this is the contours in the y space. So, if we transform x to y in such a way that for the same objective function, the Hessian matrix in the y space is a identity matrix. Now, if we are able to do that, then we can apply steepest descent method in this case and get the convergence in one step. Now, how do we do this transformation? So, for that purpose, we need to look at this matrix H. Now, suppose if we can write H to be L transpose using the Cholesky decomposition of H, and then to convert x to y, suppose we use a transformation which is suppose the following. So, L minus transpose x here, and then we have x transpose then suppose if we define y to be L minus transpose x, then what happens? So, then this expression, so what we get is a transformation to the y space. So, because this L transpose and L minus transpose get cancelled, and L inverse L will get cancelled, and what we get is a circular contour. So, we will see more about this now. So, let us consider the Cholesky decomposition of the matrix H, which is L transpose, and let us define y to be L transpose x. Now, if we define y like this, then the function f x gets transformed to the function h of y, and the h of y is defined as f of x, and x is nothing but L minus transpose y. Now, if we do this, then h y is nothing but f of L minus transpose y, and now if we apply the definition of usual definition of f of x. So, what we get is y transpose L inverse H L minus transpose y. This should have been y, and this also should have been y, and then what we get is L inverse L is identity, and this is identity, and therefore, what we get is half y transpose y. So, if x is written as L minus transpose y and h is decomposed to L L transpose, then because of the nature of this factorization, what we get is that these terms get cancelled, these terms get cancelled, and finally, what we get is y transpose y. So, because of this transformation, we were able to transform the points here in the x space to y space, such that the original contours which were elliptical, they get converted to the circular contours or the spherical contours in the high dimensional space, circular contours in the 2-dimensional case. And that was possible because of the way h was decomposed and the transformation x was done like x was transformed to L minus transpose L inverse transpose into y. So, because of this transformation, the things become easier, and then one can apply the steepization method here. So, this is the transformation that took place. So, here we have also included the term c minus c transpose x. So, L inverse transpose y will replace x in this expression, and so therefore, what we have is something which is very nice, as I mentioned here earlier, that L inverse L will get cancelled, L transpose L inverse transpose L transpose inverse will get cancelled, and finally, what we get is a quadratic in Y, where the Hessian matrix here is the identity matrix. Now, that is very important, because now if we apply the steepest descent method in the y space, so what we get is y k plus 1 is nothing but y k minus gradient of h of y k. That is a standard steepest descent method with alpha k equal to 1. So, we are not using any line search in this case, or in short we are just setting alpha k to 1. Now, if we expand it further, if we take the gradient of h with respect to y, it will be L inverse into gradient of f of L transpose inverse y k. And now what happens in the x space? So, if we want to consider that, then what we have to do is that we have to pre-multiply the whole quantity by L transpose inverse. So, if we pre-multiply this expression by L transpose inverse, then what we get is L transpose inverse into y k plus 1 is nothing but L transpose inverse into y k minus L transpose inverse into L inverse gradient of f of L transpose inverse y k. So, now what happens here? So, what is this quantity? L minus L transpose inverse into L inverse. Now, if you look back, the way H was defined was LL transpose. So, if we take a inverse of this quantity LL transpose, what we get is L transpose inverse into L inverse, which is the quantity here. So, this quantity is nothing but the inverse of the Hessian. And what are these quantities? these are quantities are nothing but xk plus 1 and xk, and suppose if you replace L minus L transpose inverse yk by xk, then what we get is xk plus 1 to be xk minus h inverse the gradient of f of xk. So, the usual gradient direction gets deflected, the usual negative gradient direction gets deflected by the matrix H inverse, and that is used to move from xk to xk plus 1 with the step length of 1. So, we have come up with a new method where instead of the usual negative gradient direction, we are trying to deflect the negative gradient direction by the matrix H inverse. Now, if we do that, then that corresponds to the steepest descent direction in y space, and this steepest descent direction in y space would converge to the optimal point in one step, because the Hessian of the objective function h y, which also corresponds to f of L transpose inverse y, the Hessian of that objective function is a identity matrix. So, if we apply the steepest descent method to the function h y, we reach the solution in one step, and that corresponds to deflecting the negative gradient direction by H inverse. Now, this method is called the Newton method, and we will study Newton method in the next class. Thank you.